third lecture in the second module. If you remember, in the first two lectures I discussed applying the basics of the scientific method as well as different types of study design in the second lecture. In this lecture I'm going to talk to you about validity and bias. And so when it comes to validity, the best definition of validity would be the best available approximation of the truth. And typically validity is a term we use to discuss the quality of the conclusions that we are able to reach based on our research study design. And so the study design becomes very important when we talk about validity. And so validity is often especially used to discuss the quality of research findings on cause and effect, on analytic studies, really the kind of studies that we're going to be interested in for answering business questions. Validity is also related to the ability of our study design to avoid or mitigate bias. And so there are four different types of validity to think about. And this comes from the Trochum reading. To the extent our study design enables us to answer each of these four questions, then we have that type of validity. And another important thing to point out here is that each type of validity is a necessary condition, but not sufficient condition for the next type. So these four types of validity really build on each other cumulatively. So the first type of validity is conclusion validity. And so this, to the extent we have conclusion validity, this enables us to answer the question of whether there is simply a relationship or association between the cause and effect variables in our study. And the cause variable would be the independent variable or the exposure variable, and the effect would be the dependent variable or the outcome variable. The second type of validity is internal validity, and this is probably the type of validity that you hear discussed the most in research. And to the extent that this exists, we are able to answer the question of whether the relationship between the dependent and independent variable is causal. So an internally valid study is one where we can determine whether or not the relationship between the independent variables and dependent variables is a causal relationship. And here, this is where we're most concerned about issues of bias, confounding, and spurious correlations. Thirdly, the third type of validity is construct validity. This is fairly straightforward, and this is simply, did we actually measure the construct that we intended to measure? Lastly, the fourth type of validity is external validity. And so here the question is, can we generalize our findings from the particular study sample or population that we conducted our research in to a broader population? And if our sample that we did the research on was very specific, for example, say we did research on white male veterans at VA hospitals, then we are very unlikely to be able to generalize our findings to the broader population. And so you'll also hear researchers talk a lot about external validity. So now I want to talk to you about bias. Bias is any systematic and non-random deviation of our results from the truth. And so I've underlined the important terms there in that bias is something that's both systematic and non-random. And this is almost always caused by flaws in the research study design. And there are always going to be flaws. So as much as we want to completely remove bias, in reality, we're typically trying to mitigate bias as much as possible because no study design in observational research is perfect. So what does bias do? Well, bias can create an observed association between our independent variable and our dependent variable that is actually not real. So it makes it appear that there's a relationship when in fact there isn't a relationship. Alternately, bias can also prevent us from detecting the presence of a relationship or association that is real. And so, as a result, bias leads us to incorrectly either reject or fail to reject our null hypothesis. I also want to note that bias is different from random error or chance. So your textbook talks about random error or chance. Random error is merely what our statistical tests are designed to handle. So when we come to talk about hypothesis testing and p-values, what we're trying to prevent here is random error. But this is something that is completely different from bias. It doesn't matter what our statistical tests or p-values tell us. If we have a biased study, our results could still be incorrect. Okay, so bias is very much related to internal validity. Typically when people use the term bias in research, they're generally referring to a systematic error that leads us to incorrectly reject or fail to reject our null hypothesis. And so the whole reason we test hypotheses is in order to determine whether there's a causal relationship between the independent variable and the dependent variable. Did the exposure to tobacco use, for instance, cause the effect of being diagnosed with cancer, for instance? And bias is caused by a flaw in our study design that prevents us from detecting true causal relationships. And as you'll recall, a study that cannot detect causal relationships lacks internal validity. And so as a result, bias implies a lack of internal validity and vice versa. And so confounding, this is a term you typically hear used by epidemiologists, and this is a type of bias. A confounder is an unobserved third variable that is correlated with both the observed cause, our independent variable, and the observed effect, the dependent variable. And so this unmeasured third variable, because it's unmeasured and it's correlated with both our independent and dependent variable, distorts the relationship if the researcher is unable to control for it in the analysis. And this creates systematic error and results that are biased and lack internal validity. And so let's take an example. The question is, does coffee drinking cause cancer? And, early on, researchers on coffee drinking were surprised to find that coffee drinkers are more likely to get cancer. And so do we really think that coffee drinking causes cancer? Well, let's think about this a little bit. These researchers also found that coffee drinkers are more likely to smoke. We also know that smokers are more likely to get cancer. And so if we measure the effect of coffee drinking on smoking without accounting for if we measure the effect of coffee drinking on cancer without accounting for the third variable smoking, then it would appear that coffee drinking causes cancer. And so in this case, the omitted third variable or the confounder would be smoking. And so this shows why it's important, why unmeasured variables can, when they're unmeasured, create all kinds of problems and systematic bias in your research study. So it's important to think about what variables you might not be measuring that could affect the relationship that you're trying to detect. And so I'm going to talk to you briefly about some different types of bias by study design. I previously discussed 4 different types of study design. And so cohort studies, which are typically the strongest type of observational study design. These, however, are also, like all the other study designs, susceptible to selection bias. And selection bias happens when a factor or variable that's associated with the outcome affects the selection of participants into the study. And so one type of bias here is referred to as the healthy worker effect. A lot of times studies use employers and employees at particular employer groups as their participants. And so the healthy worker effect exists because in general, the working population is healthier than the non-working population of a similar age. And so this creates a systematic difference in this population that may also be associated with the outcome, in particular if it's related to something related to disease status. There's also the issue of volunteer bias. If people volunteer for a study, there might be something systematically different about the kinds of people who volunteer for a study than those that don't. And this could also be associated with the outcome variable. For instance, perhaps people who volunteer for a study are more proactive in life in general, and also more proactive about their health and monitoring their health symptoms and going to the doctor when needed. And then lastly, another type of selection bias is loss due to follow-up. So people who die, for instance, or people who do not, if it's multiple waves of a survey, people who do not continue to fill out the survey and mail it in, there might be something systematically different about those people, and that would be selection bias. When it comes to bias in cross-sectional studies, the bias people are most concerned about, because these are surveys, is response bias. And so response bias is a type of selection bias, again, based on survey response. Do the type of people who respond to surveys systematically differ from those who do not respond? Probably those people do. When it comes to bias in ecological studies, I mentioned before the ecological fallacy, and so this is incorrectly assuming because two things are associated at the group level that applies, that those things are true at the individual level. And lastly, when it comes to case control studies, there are two particular kinds of bias I want to draw your attention to. One is observation bias, and so this has to do with incorrect measurement. So because we're going back in time, we're hoping that the data, people were selected based on being cases, and then we have to go back in time to get the antecedent variables and exposures. And so the data might not be good, and so that creates inaccurate measurement. Or frequently we're relying on people's memories when we go back in time, and so that brings up the issue of recall bias, and that people might not be able to remember everything that happened to them. And in particular, we're concerned if there's some systematic difference between cases, say cases where people with Alzheimer's disease, their recall might be systematically different from controls without Alzheimer's disease. Lastly, again, there's the issue of selection bias. So typically, cases and controls are selected from in hospital settings, and it's highly likely that those who are selected because they visited the hospital are systematically different from the rest of the population.